Hello, friends. Welcome to episode 5 of Kermit GNC. So far, we have developed our 6 degrees of freedom Cessna like airplane model quite a bit. Today, we will aim to integrate the elevator trim condition onto our airplane model. So, let's get started. With the trim algorithm, I will show you how the algorithm is derived, how an automatic trim motor can be integrated into it, and we will also put some rate limited trim conversions. In the end, we will try to look at our elevator deflection parameters and therefore the pitch angle plot to see how good the airplane is able to trim itself. So back at our model, this is where we stopped last time. So this is a continuation of all of our work from before. If you have not gotten a chance to take a look at the previous episodes, I highly recommend starting from episode 1 in this series so you can at least get an idea of what we are doing in today's episode. Alrighty, now let's see. Trim algorithm. We will develop trim algorithms. So let's go inside the moment subsystem, double click on that. Let me show you the trim algorithm derivation first, like I always do. So that's not the one. Let's see. Okay. So that is the derivation that goes into elevator trim algorithm. So this formula may look familiar to you because this formula comes from our CM formula from before. That is the pitch moment coefficient that includes pitch damping inside of it. Now, it's the same formula, but for trim, you want to set your CM equal to 0 because CM is directly connected to your pitch moment, and whenever you trim an airplane, you don't want to introduce any more pitch moment. You want the pitch moment to be 0 so the airplane is able to hold itself with that attitude and altitude that the pilot commands, hence called trim. So CM is 0. If you set that and solve this equation for your del E, the obtained del E would be your trim del E, that is trim elevator deflection needed. We will take this, we will call it trim offset. So we will take the offset that is found with this formula and we will add that offset to the pilot input from the elevator deflection. Together, they will give us the new elevator deflection command for the rest of the model. So that's the idea. Let's implement it. So most of these parameters are already existing in our moment model here. We can reuse them. Let's do, so I want to work on getting my numerator of this formula. So that has 2 of these parameters being added with each other. So let me start with a sum. Okay. One will take the CM alpha times alpha. So there goes that. And if I highlight this channel, you can see this channel contains my CM alpha times alpha. And the next one will go to the CM Q or CM underscore Q if you want to name it differently. Now, if I highlight this channel, you can notice this has the CMQ times C over 2 V safe coming from the top times our Q. So those are giving us this addition at the numerator. Now we need to negate it because of this negation sign. So I can use again to negate it. Let me do -1. And then I gotta divide all of that with CM del E. So here is this one. Now CM del E is right there, but it's a gain block currently, and that will not allow me to directly connect my signal to CM del E because this is multiplying with del E input. There are multiple ways to get around this issue. What I am going to do is I will remove the gain block, and instead I will use a constant block, rotate that, and call that to be my CM del E, make that -1. And so now I will use a product, rotate that, and I can just multiply both of these signals. So that will preserve the old model without any disturbance, but it will allow me the flexibility to divide this directly with CM del E. What I get out of this is my trim offset. So I can say elevator trim offset. Now I will connect this with a go-to block. Let's name that better. So I will say del E trim offset, tag visibility global, apply. Okay, I can make that longer so you can see the name. All right, so that is the basic formula coming from this derivation. Let's go to the top level. Now we will implement that trim offset onto our pilot command del E coming from this slider. So let's get a from block. Here is del E offset. You can make that longer to catch the whole name. And I will delete this signal, add a sum to it. That way I am able to connect both of the pilot command del E and trim offset del E onto the same thing. While I am here, what I will do different is I'm going to double click on the slider. I will change the range for my stick elevator's input. I will make it -0.5 to 0.5. That is a reasonable range, keeps us around 30 degrees, 40 degrees range, like that. We don't want to exceed that because then we are going to literally break the model. So that looks good. And before I initiate any test, let me make sure that my rudder is neutral and aileron is almost neutral, because I don't want any lateral directional dynamics to affect me at this point. And throttle, since my max is 2500, I will just take it about 1400 off that. So there is the fractional reduction. Okay. And let's double click on this 6 staff Euler angles block. Make sure everything is as we need. So all the other parameters are 0. I have some initial forward velocity and of course initial mass and inertia matrix. With that being said, why don't we just give a quick run to this? Let's just keep it 30 seconds. And I'm going to open my Euler angles scope so we can see the real time performance. Let's see if this is going to be a smooth run or not. All right, looks like that went pretty good. And you can see there is some lateral directional dynamics showing up. What I can do is click on these legends. That way I can turn them off for now because I want to focus on my longitudinal dynamics right now since I'm trying to do elevator trim algorithm. So looks like it's not stabilizing itself. You can see all these oscillations popping up, which we don't want that. So why don't we go ahead and troubleshoot it like usual? If I wanted, I could do these troubleshooting outside of this video and show you the clean and nicely performing model, but I don't want to do that. I want to do this kind of troubleshooting with you guys so you will take advantage from it, and you are not just learning how to do pristine models, you are also developing the troubleshooting skills along with it. So All right, let's see. Let's troubleshoot. So what we will try is, since we are not getting any errors at this point, we are going to go back to our trim algorithm, and we can actually put a scope. Most of this troubleshooting with these kind of wiring, when it becomes too many blocks like this high level of a model, would need you to just scope different parameters at different places repeatedly. Okay, so the trim offset is giving me values that are oscillating. That is definitely not looking like what I want. So looks like it's trying to chase itself. Now, if you notice, this is the trim offset, and this is the actual pitch angle. So if you notice, it's kind of like this trim algorithm is trying to chase this difference, with every cycle. And so it's like thinking like a dog is trying to just chase its tail in circles and circles. Well, we don't want that. So let's get rid of this scope, because once you are done scoping at a point, you may want to just remove the scope so it does not burden the model when it runs, because that can affect your running time and performance as well. All right, what I would do different is, let me put trim motor algorithm into the trim algorithm. So this is the idea. Once it shows up, well, what that trim motor will do is it's gonna help me to only push fraction of the offset, trim offset, and not the entire trim offset every single time. So this is the idea. So I'm gonna take the difference between my actual desired trim and the offset and take a fraction of that added to the offset. So let's actually model this, and then we will try to see if that will help improve the performance. So my trim old here is my desired or trim offset, right? So let me get rid of this signal here once it will let me. All right, now my trim desired is what is going to come from this. So let's start with a unit delay. I'm going to put a delay because I want this to apply with a slight delay. Double click on that. Initial condition can stay at 0. Now you notice this is a difference. So I want to get a sum block, double click, and make one of these signs a negative. I am going to just rotate this for convenience sake. Alrighty. Now the old one, or this is my old or offset coming from this, that is being negated. And my new one is going to come from this from before. So I'm going to move these aside a little bit. And then I would not worry about making this look nicer. I'm going to try my best to stick to the, good practices I do. But if it becomes not too nice at some point, it's okay. Focus on making the model work first. Once it works, you can always make it nicer and cleaner. All right. So what I will do is I'm going to put another unit delay here. So that's the delay with the initial trim offset, and that will go into my difference. So those are those two. Now I'm going to put another K or gain, so I can capture a fraction of that difference. So here is that gain. I can call that to be, all right, once it will let me name it. There we go. So their gain can be 0.01. So I'm just taking like 1% gain at this point. Here is, if you make it longer, you can see the value. Let me call that trim motor gain. Okay. And now I need to add both old and the fractional trim motor gain. So use another sum. We can rotate that as well. There is one coming from that, and another one is this old guy. Okay. Once we have those, I will just add this to this unit delay. That completes my trim algorithm along with a motor in our automatic motor in there, or automated motor, whatever you want to call it. I am going to make a subsystem out of it so I don't um, increase the clutter on this screen. Every time you have some work done, it's a good practice to keep on hitting that space bar every now and then, because that helps in auto adjusting the whole model fit to the screen. Okay, I am going to name this elevator trim. Alrighty, that's that. It will not be a bad idea to double click and just name these connections. So, for instance, this is del E trim offset. And then these are, let's see, this one was CM alpha. So I can call it CM underscore alpha. So I don't confuse this with my CM alpha coefficient, derivative coefficient. This is CM del E, and this would be CM underscore Q. Again, not to confuse with my CM Q derivative coefficient. Okay, so once you do that and make it longer, you can see the names on the subsystem icon, which goes a long way, like that. Okay, now that is a better trim algorithm with the automated trim motor inserted. So we can give that a run again. Let me have my Euler angles scope here. I'm going to run that. Okay, looks like it's getting better, but again, I do see some oscillations. Let's go into my trim algorithm. Let's try to scope some of the things here. What I'm going to do is, if you remember, I mentioned once you apply this trim algorithm, the goal is to get a CM of 0, which means CM connects directly to your pitch moment, and that should be 0. So here is my pitch moment. I will try to scope that pitch moment. So let's try to scope the pitch moment right there and see what's happening with that. So if I run this, okay, and that is not 0. So my problem is not in the trim algorithm at this point. I would guess my problem is going upstream onto my pitch moment here. So that has 4 different things, if you recall. This is Q bar, and S and C mac, those are constant numbers. I wouldn't think too much issue with those. C bar is again pretty straightforward, so wouldn't think too much about that either. This one is actually CM. Since CM has a lot of things inside of it, I would actually try to trace back into that. So I'm going to make sure, first thing first, that all my derivative coefficients are all looking good, sign convention wise and value wise. So that is a negative 0.1. Okay, alpha is coming from the other system. CL del A is a positive, it needs to be. CL beta is negative 0.08. Cm del E is negative 1. Cn beta, that is the, okay, Cn beta is your weather vane stability street name. And, oh, okay. So that should be a positive, because you want your airplane to yaw into the wind. A stable airplane would yaw into the wind, pitch into the wind, roll away from the wind. So with that being said, why don't we give that a run? So here is my Euler angles plot. All right, massive difference. Very nice. Looks like pitch is increasing in the negative direction, or decreasing. Well, if you remember, our convention that this six-staff Euler block uses is downwards is positive, right? So this one is negative, which means it is pitching up, and it would actually match, because if you notice over here, I have given a positive pitch there. So, well, I did take care of changing the sign convention when I was doing the aerodynamic block set. And if you remember, we were fixing the sign convention with these negative signs. So that means let's make sense of all of this. If I give a positive elevator deflection, which means this airplane is pitching down, and I think for a normal airplane, if you are the pilot in the cockpit, that would make sense, right? If a positive elevator deflection, meaning you are pushing the stick away from you, which means the nose of the airplane is going down, hence your pitch angle is going down. I think that makes sense. With that being said, it's stabilizing but coming down, but then going back up again. So let's see if all of that makes sense again. So what I'm going to do is I'm going to scope my PQR, which does include the Q, which is my pitch rate. Let's run that. Okay, so let's get our legends, and I'm going to turn yaw and pitch rates off, because yaw and roll rates off, because I want to just focus on pitch at this point. And if you look, this pitch rate is decreasing and then increasing again. So if pitch rate is changing, it would make sense that my pitch angle is changing accordingly, right? So that's looking like my trim algorithm is working. Now, if you notice, this is the scope I put for my trim offset. So it is trying to give some offset. All this oscillation here, well, you see that because the trim elevator is trying to put 1% of fix every time of the pilot command, right? What we can do is we can go back to my elevator trim algorithm, and instead of 1%, I can call that to be a 0.1%. So now if I run this, look at this. So this is the scope I did put for my elevator deflection. Well, let me get rid of that scope. I'm going to actually put a scope here. So that would give me my trim offset. Excuse me. Let's name it. You always want to name these scopes, even if you use it for once, because otherwise everything is going to say scope, as you just noticed, and you would not know which one is which. All right. So since I put a new scope, I am going to run this, and looks like I do see steps, because again, it's trying to achieve the desired trim in steps, which would make sense. So why don't I increase this to maybe 0.05, like 5%? Let's run that. Okay, still see these steps. Let's try 0.05%. If, let's see, so running that one more time. All right, so this is trying to achieve things in steps, which is not a problem, but I was just playing with that parameter to see how it improves or degrades the trim offset value. Another thing is the M, right? Here is my MY, which I am expecting for that to be, like I said, I'm expecting MY to be approaching to 0, basically. So MY, let's see what's, okay, it's taken, doesn't like that. I'm going to say M pitch, then M pitch, which is my pitch moment. Let's run that and see what we get. So pitch moment. Okay, coming back here, running this one more time. So looks like it is coming to 0, which is a very good sign. but it's coming to 0 with steps. So let's keep playing. So elevator trim, this is, what if I make it 0.005? And honestly, you can't get enough of this. Would you would want to play with all these variables several different times in order to be able to, see what each one of them do. Okay, that's looking much smoother, right? So looks like this parameter does help. So if you play with that, you are basically just trying to take smaller bites in order to get to the desired trim, which is a good sign because you don't want your trim algorithm here to behave like a controller for your pitch angle or any longitudinal dynamic. This is not a controller. This is just a pitch motor helping you to automatically adjust your airplane and get it trimmed. And that's that. So, with that being said, let's actually go to the top level and make a good sense of all of this. So, looks like my or my elevator trim algorithm is all good now. One last thing I would try to do is I'm going to set this timer to infinity, and then I'm going to get my Euler angles scope. And now I'll just keep it side by side. This is another way you can play with this to do some analysis. Now what I'll do, I'll keep my elevator, like I'll give it some positive deflection, but as it runs, I want to try to change the deflection and then can stop it. And now let me see the entire profile. Okay, looks like with every change I made, it tried to trim back to 0, and finally it's able to again trim back up to 0. Okay, so that's like that is taking my pilot command and bringing it close to where I want it to be. That looks promising. So that's another way you can play with this thing. Okay, in order to end this video, I would share a couple of thoughts. So we did so many things with this model in these 5 episodes. It may be a good idea to just take a look at how far we have come and what all things we can implement, which is coming up, right? So let me see. I have actually made a document and deleted that. Let's open that so I can share with you. Let me actually, that's better. So we have achieved that with this low fidelity aircraft model, we have achieved establishing flight dynamics foundation with our 6-top Euler's block, aerodynamic modeling, which involves airspeed, angle of attack, side slip angle, dynamic pressure. Longitudinal dynamics include all the stability derivatives in them. Lateral directional dynamic, we did model some of the basic things. We are going to improve on that. Propulsion does have throttle formula in that. Again, rudimentary book level throttle formula, but that does the job. Flight controls, we have put those, and now we have put the trim system onto it. And we did achieve some stability at this point that we could achieve. Now, what is still missing, right? Big question. So a big one is side force aerodynamic, which please expect that in a future video. So once we put this lateral force dynamics or side force, which is CY, it's going to improve our lateral directional dynamics a whole lot. That would actually help us to analyze things like slips, skids, crosswind effects, rudder generated lateral acceleration, and Dutch roll behavior. Other things coming up would be stall modeling and additional stability derivatives like CLR, CNP, CL-del-A, adverse yaw effects, robust engine dynamics, which would take into account engine spool up or spool down, and atmospheric effects. I would highly recommend all these stability derivatives. If you don't know their street names, you want to practice with that pretty much as frequently as you can, so it becomes a second nature to you with stability derivatives doing what for the airplane. One last thought is, you may ask yourself, if this is low fidelity with all of these ingredients we have put, what is medium fidelity and what is high fidelity, right? So to share with you, these are all low fidelity. And if you have noticed, we have literally defined all these stability derivatives as gains or constants here. So with medium fidelity, you would not have these as constants or gains. You are actually going to use lookup tables for them. And those lookup tables will convert these things into functions of a specific parameter. For example, this one here will become, so you know how this CL alpha, this is a constant now, that will end up becoming a lookup table, which will give you CL as a function of alpha. So that way everything will become a function and lookup tables. And with high fidelity, it will be lookup tables, but not as a function of one parameter, alpha, for instance, but it will become a lookup table with a function of 3 or 4 different parameters. So again, giving you that CL example, you would be able to have a lookup table that will give you CL as a function of alpha, beta, Q, and multiple things like that. So that way you would be able to account for things like stall behavior, things like engine spool effects, and very minute effects like that, which will in a way help to increase the fidelity of your model. One last thought: with the flight simulators that are developed in these companies out there, they function with about tens of thousands of, or maybe 10,000s of these derivatives all around in their model. And they are responsible for constantly using flight data, real flight data, to tune those parameters all at one go in order to make one model work smoothly. So that's how far it gets, which may intimidate some people, but if you are into it, it may excite you as well. All right, hopefully that was all fun this time. I will see you in a future video with new material added to this model.